Hello everyone, welcome to this week video tutorial. Today's topic is work example of crank slider. So in this video we'll analyze position, velocity and acceleration for crank slider using vector loop approach. Alright, so if we just look at this short video clip where we can see this is a crank, this is a slider, and the crank is moving. As a result, the slider slides from left and right direction horizontally. So if we want to just recap the general link name, so this is D, which is the distance between the fixed point of the pin joint where the input link or crank is connected, and the center of the slider. So fixed point and the center of the slider, the distance we call this slider distance, which we denote as D. Because this is the driver, so we consider this is an input link, which is link length A. This is a coupler which connects input and the slider, and we consider this link as B. And finally, the vertical direction from the slider to the center line of the fixed joint we consider is offset, which is C. Alright, so let's consider that input length is 3.5 millimeter, coupler length is 12 millimeter, offset is 4 millimeter. The input angle is given to us as 30 degrees. The crank or the input is rotating at counter direction. So let's consider the angular velocity is 10 radian per second and the angular acceleration is 0. Okay, to solve this problem, we need to consider a few stuff. For example, we need to consider all dimensions are in millimeter and the angles are in degrees, and we need to find angular velocities and accelerations of coupler link and slider. That means we need to consider the angular velocities and acceleration of link 3 and the slider, which is omega 3 d prime and alpha 3 and d double prime. Velocities of pin joints. So velocities of pin joint means this pin joint A and B, so we need to find linear velocities of pin joint A and B, which is VA and VB, and also we need to find linear acceleration of pin joint A and B, which we can denote as AA and AB. Alright, so for crank slider, when we want to find theta 3, this angle, the equation is given to us, so we need to just substitute all the values and then we can find the angle as negative 10.8 degrees. Now for crank slider, this is really important, is to remember that the angle we calculated using this equation is for crossed configuration. If we have open configuration, then we need to subtract that calculated angle from 180 degree. So if we can recap our last tutorial where we discussed that even though we got limited resources as a reference to identify open configuration and cross configuration for crank slider, so from that limited resources, but I realized that when the slider is on the left side of this y-axis, then we consider as open configuration. When the slider is on other side, that is left side of the y-axis, then we consider that is cross configuration. So we can see that this configuration that we are dealing with is open configuration. So according to these equations, our result will be 190.8 degrees. So when we need to find a slider position, we need to use theta 3 for open configuration because our system is open configuration, and considering that angle we get d equals to 14. So once we find theta 3 and slider position, then we want to find angular velocity for length 3, and the equation is given to us, so we don't need to remember these equations. We just put the value, substitute all the values, and we find the angle is negative 2.06 radian per second. Using all the equations and the values that we know, we can find d prime or velocity of the slider. So the velocity of the slider we found as negative 9.37. Now we can say that this is equal to linear velocity of pin joint B. Why? If we can just look at this diagram, so you can see that the center of the slider, this B point and this point are actually the same point. So when the slider moves left or right, this point also changes, which means d values actually changes when the slider changes. So that means if we find the velocity of slider, that would be the velocity of pin joint B. So this statement is very important to remember, that when we get d prime's value as negative, the angle should be 180 degree. When we get positive, the angle should be 0 degree. How? If we just look at this, and if you can remember the definition of measurement angle for the vector, we measure the angle at the root of the vector with positive axis counterclockwise. So when the slider goes left side, that means it makes 180 degree angle with positive x-axis counterclockwise. When the slider goes right side, then it is going towards the positive x-axis direction, so the angle should be 0. Alright, so based on this information, we can say that the linear velocity of pin joint B magnitude is the magnitude of this one, absolute value of this value that we get from d prime, and the angle should be 180 because we get negative sign. Alright, so that is our first part answer. Second part, where again angular acceleration of coupler link, the equation is given to us and we know all the values, so we can substitute them and we can find the angular acceleration of link 3 is 9.11 radian per second square. Remembering this equation, when we calculate d double prime, we get this value, which we can directly say this is the linear acceleration of pin joint B. So the magnitude and angle should be, first of all, the angle should be 180 degree because we found it's negative, and the magnitude of linear acceleration of pin joint B should be the absolute value of d prime, which is 264.49 millimeter per second square, which is our another answer. To find linear velocities of any point, first we want to start to derive the equation for any pin joint. So let's consider this is x and y axis, and OA is a vector whose length is r, and it makes an angle theta with positive x-axis counterclockwise. So for OA, the position vector can be represented like this: the length of this vector, which is r, times ej theta. So if we differentiate this r with respect to time, we'll get linear velocity, and with differentiating this part, we'll get r e j theta times j e d theta by dt. So the final polar form equation would be r omega j e j theta. So that is our polar form. By definition, we know that d theta by dt is omega. So if we want to convert this polar form into Cartesian form using Euler's identity, then we get this equation, this form. So considering this equation, let's consider for pin joint A, linear velocity for pin joint A, which is related to, this is pin joint A, so this is related to link 2, whose length is A and the angle is theta 2, and the angular velocity of this link is given to us as omega 2. So we can write VA equal A times omega 2 times, in parentheses, sine theta 2 plus j cos theta 2. If we want to substitute this value, the equation becomes, so after calculation we get the value as a complex number, which is negative 14j 24.25. Now we want a magnitude of this number, which give us as square root of these two terms, so negative 14 square plus 24.25 square, which give us 28 millimeter per second, which is our one answer. Now when we want to consider the angle, let's consider with calculating the angle first. So tan inverse 24.25, which is y, or imaginary part, divided by real part, and the angle, calculated angle, is negative 60 degrees. Now let's draw the tiny diagram where x-axis is real part and y-axis is imaginary part. So if we look at our real part is negative, so it would be somewhere here, and our imaginary part is positive, so it should be here. So the angle, so the vector we get is VA, this angle, and the angle we calculated here is 60 degree. However, according to the definition, we need to measure the angle with positive x-axis counterclockwise, which should be this angle. So our angle should be for linear velocity at pin joint A would be 180 degrees minus 60, which gives us 120 degrees. This is our 120 degrees, and that is our another answer for linear velocities at pin joint A. Now when we want to find linear acceleration of any point or pin joint, then again we need to derive the equation for linear acceleration. So we can start from linear velocity, as linear velocity's polar form, where we find r omega j e j theta. Alright, so when we differentiate this linear velocity with respect to time, then we'll find linear acceleration, and we need to differentiate this term as well. So r omega j e j theta. Now here r and j, they are constant, they do not change with respect to time. However, omega and theta, they changes and they change with time. So let's differentiate these two parts with respect to time. So when we differentiate these two parts, we get this kind of form, which actually gives us UV differentiation. As you know, U times V prime plus V times U prime, this kind of differentiation. So after the differentiation and after simplification, we get the equation for linear acceleration as Rj omega square j e j theta plus alpha e j theta, which is a polar form. Now we want to convert these into Cartesian form using Euler identity. So after introducing that term, the equation becomes r omega square j square cos theta plus j sin theta plus r alpha j cos theta plus j sin theta. Now when we multiply this j with this term, this j square with this term and this j with that term, the ultimate or finalized equation will look like this: negative r omega square cos theta plus j sin theta plus r alpha negative sin theta plus j cos theta. And that is our final form for linear acceleration at any point or pin joint. So if we want to find linear acceleration for pin joint A, which is relevant to link 2, as you already saw just a few minutes ago, so we can just substitute the value, which we can write like this. So linear acceleration of pin joint A, which can be denoted as AA, and we can write negative A omega 2 squared cos theta 2 plus j sin theta 2 plus A alpha 2 negative sin theta 2 plus j cos theta 2. Alright, now substituting all the values that has been given to us or that we calculated, the ultimate results as a complex number will find as 193.99 plus j112, which is a complex number again, and we want magnitude of this linear acceleration, which give us 224 millimeter per second square. In terms of angle, let's find the angle first, which is negative 112 divided by negative 193.99 and gives us 30 degrees. Let's draw the diagram one more time, where x-axis is real part, y-axis imaginary part. If we just look at our complex number, we can see that our real part is negative, our imaginary part is also negative. So the angle we are expecting is in this third quadrant, which is a vector, and the angle we calculated is this angle, 30 degrees. So again, according to definition, the angle we need to consider or measure is these angles, which give us AA angle as 180 degrees, the whole angle plus this calculated angle, which is ultimately give us 210 degrees. So yeah, that is our answer for linear acceleration of pin joint A. So for crank slider solution, just remember that for angular velocities and accelerations, all the equations will be given to you. For linear velocities and acceleration, you need to derive the equation and then find the value. Hope that will help you to understand how to solve a simple crank slider problem. See you next time.